Good morning, everybody. Welcome to the last day of the AICT Atal-sponsored Faculty Development Program titled Innovative Micro and Nanotechnology and Fundamental Principles. This is organized by Department of Mechanical Engineering, HIT Haldia. So let us first welcome the dignitaries of the dais. Professor Subrat Kumar Mundal, Principal, Haldia Institute of Technology. Professor Torun Kanti Jana, Dean of Engineering, Haldia Institute of Technology. And I will request our principal, sir, Professor Mundal, to felicitate Professor Ghosh with flower bouquet and with the wreath. Okay, so we are set to begin the technical session. So before today's eminent speaker takes the stage, let me give a brief bio sketch of the expert. So Professor Amitabh Ghosh is currently serving as the professor in the Manufacturing Engineering section of Indian Institute of Technology, Madras. Professor Ghosh has received his PhD degree from IIT Kharagpur. He joined in the Indian Institute of Technology, Madras in December 2008 as an assistant professor after serving in the Indian Institute of Technology, Guwahati for 1.5 years. Professor Ghosh has expertise in the field of high-speed machining and grinding, active brazing of ceramics, and advanced PVD coating technology for cutting tool applications. He has already guided so far 5 PhD students, 3 MS students, along with 21 MTech students. Presently, 10 scholars are working under his supervision. His current research activities include development of new generation nano composite coating, machining with nanocrystalline diamond coating, micro lubrication technology for machining and grinding, precision joining of CBN and diamond metal substrate, and laser brazing of diamond. He has about 70 publications in international and national journals of repute and conferences with I-10 index of 30. He has 5 patents which has been filed from his research group in the domain of active brazing, grinding, and nanofluid for machining applications. He has several industrial and sponsored projects to his credits. He was awarded the Young Faculty Recognition Award from IIT Madras in the year of 2018. He is also a regular reviewer of many journals of international repute. So with this brief introduction, let me welcome Professor Ghosh for his lecture.
Hello, 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 hello. Hello, hello. The last bench, am I audible? Yes. Oh, that's a loud voice. Very good. Yeah. Good morning, everyone. It's a reasonably decent gathering. I can see a lot of energetic, motivated, spirited face. Of course, you are all sitting in the behind, but okay. It's a great pleasure to be here at the Institute of Technology, coming from Indian Institute of Technology, Madras, and I'm really grateful to Professor Professor Gautam Ghosh, and all esteemed faculty members of your department. And really, it's a great privilege to be in front of you. And of course, I'm always happy as a teacher, as a researcher, if I can bring some of the happenings which are there all around the world in front of you, which is quite relevant to the industries, right? So we're all engineers. The day we start with certain things. Whatever products you use, whatever things you do, very much connected to many amenities which are basically the product of our engineering applications. There is a basic difference between the scientists and the engineers. The difference is, it is a way scientists they build the fundamentals and they from there they try to see how it can be connected to the practical applications. Engineers we start with our requirements, what we need, what is necessary for our day-to-day life, or what is necessary to advance the current technologies or anything from its current state of art, and then we look for the solution and we try to get the solutions from the application processes, right? So that is the very basic differences. That is, these slides are only for the students, not for the faculty members in front of, because, yeah, anyway, I don't like to take too much time from those introductory things. Let me just go directly to the topic, whatever I've selected for you to share with my experience over the years, last 10 years. So we are working in the area of the machining exclusively, and a part of that particular area does include grinding, right? We know about the grinding, right? Grinding, you're all manufacturing students, especially you are all mechanical and you know the manufacturing very well. Grinding is considered to be a finishing operation majorly, right? Of course, that status is no more limited to the finishing operation, but still we recognize the grinding as a finishing operation. And that is so relevant to this lecture because this is going to be the finishing lecture, perhaps the concluding lecture of this series. So that way it has a good similarity. The topic whatever I selected here is microgrinding process, the next generation microgrinding tools. So if you look into the application fields, right from the biomedical sites to different aerospace component, you can see a lot of miniaturization is taking place, and there is a demand to produce the micro components. And whenever there is a micro component, it does contain the micro features. Not necessarily always the micro components are the micro micro features. It can be also your macro components having the micro features, right? So whenever we say micro machining, it is all about machining a part or manufacturing a part feature on the part, which is which are basically microscopic in the dimension. At least one feature what is produced in the micro machining has to be microscopic in the feature, in the sense that it is sub-millimeter level. Again, the definition of the micro is micro machining, in that say the micro feature of a part, that is also changing over the time. People are talking about just a sub-millimeter level is a micro. Now people are talking about all about you have to come to the level of at least 100 micron level. Otherwise, people don't consider it to be micro, because people have already entered into the domain of the nano. So things are advancing, but anyway, from that broad field, we have taken up this particular small topic, which is a micro. It's very small in the name, but it's not so small the moment you dive into it. It's like a small particle is very small. If you go to a internal feature of the anatomy of the particle, you go into the atoms and atomic network, that is, within the small you have again a universe existing. So for anything, any topic you take up, it is not very small. If you really dive into the deep of it, try to find the nectar of the science, it is all about, the grinding process, and especially it is micro grinding, and any machining operation you cannot think of without a tool and a machine tool. You need a cutting tool, you need a machine tool, and you have the workpiece to machine, right? And you need to know well about the mechanics involved into the human process. Okay, so we'll start with little basics, then we'll go into the micro. So you can see the grinding is taking place. It's a flat surface grinding, reciprocating type. The grinding wheel is rotating. Generally, it is rotated at a very high velocity. Unlike the other machining processes like turning, milling, where we set the cutting speed in the meter per minute. Like we say, even if you say 500 meter per minute turning speed, 500 meter per minute milling is very today. Not just 30-40 meter per second. We talk about almost 100-150 meter per second. That means if you convert a 150 to 60, right? So almost 150 to 60 means almost 9,000 meter per minute. So it's a huge amount of velocity. If you see macroscopically, this grinding wheel is the cutting tool. It is grinding the material. But if you look microscopically, the interaction is taking place between the grains and the workpiece, right? And especially you can see that these grains here, you just see one particular grain. Here, the cutting velocity is over here. The beads are in contact with the maximum uncut shiftiness. Okay, so this uncut shiftiness, it can be formulated like this: 4 by CR, BW by BS, A by DE into power 1 by 2. Again, root of the entire thing, right? So what happens? Let us just take an example. You should do the fine. Is it okay? Fine. Right. So let us come to the cutting action of one particular grain. Right. One particular grain. So this is about to start machining and it is leaving the workpiece with the maximum uncut shiftiness. Right? So why I am taking all these things, let us just take a practical example. How do you do it? You have to set the speed, feed and depth of cut. So the grinding velocity, you can just set at 30 meter per minute, 30 meter per second, a depth of cut in the order of 40 microns say, and a table speed say 3 meter per minute. Right? But this is all about the very macroscopic view. Microscopically, one grit is removing the material and one grit is penetrating into the workpiece by this much thickness. This is the typical shape in 2 dimension of the chip which is getting removed from the workpiece. And if you just see the formula here, this HM is nothing but if you just take a perpendicular distance from this point to this curvature. Okay? So now what happens, if you calculate these things with this BW, VH, A and DE, what is A? A is the depth of cut of the downfield and D is the equivalent diameter of the well. So anyway, here it is the diameter of the well. So this particular value comes down to the order of this micron. Although you are giving a depth of cut of 40 micron, the grid penetration depth comes back to the order of only 2 to 3 micron. In a grinding process, if you are in front of a reciprocating grinder, you give a depth of cut of 30 microns, but ultimately, effectively our grid is penetrating only 2 to 3 microns. This is necessary because the grinding wheel, if you look at it, on the periphery of the grinding wheel, the exposure of the tip from its bond is only few microns, just maybe 30-40 microns. With that, we will not be able to accommodate 40-50 micron depth of cut. So eventually, you have to make it in such a way that the grid penetration comes to the order of few micron only. Okay. So now, why I am telling all these things? Although this is a macro grinding operation, but essentially the grinding is a micro machining operation because you are giving a depth of cut at 40 micron, but the grid is even taking a infiltrate or the radial penetration depth only 3 to 4 micron or just 2-3 micron. So it is grinding process as such, it's a micro machining operation. But when we say it's a microscopic interaction between the tool and the work, but still we don't say today it's a micro machining. Why? Because really in this process we are not producing a part with any feature dimension equivalent to your microscopic. That is not there. We are grinding over a width, maybe just a 4 millimeter, maybe just a 5 millimeter, that kind of thing. So essentially, we really don't say, we do not categorize grinding into the micro machining group. But its removal process is very much involving microscopic volumetric removal of the material. So this is very much fundamental and very much textbook information. But now we'll be going into the practice and we'll be seeing what the industry demands and what is the current requirement, how the things are happening. So now I will just hello. Hello. So essentially, if you look into the removal process, the removal mechanism involves typically three. One is rubbing, another is ploughing, and another is shearing. Right? So if you just look at it. So this is a grinding wheel. A very specific grinding wheel. It shows that on its layer there is only one layer of abrasives on its periphery. Okay, it can be CBN, it can be diamond. Since it is only one layer, this kind of grinding wheels are basically prepared with CBN and diamonds. They are called single layer wheels, but it doesn't matter to understand the mechanics of the removal. If you just take this image, you have the super abrasives surrounding it. These super abrasives are removed in the material, right? They can remove this in rubbing, in ploughing, and the steering. Okay? So this is typically, if you just look into the orthogonal cutting operation, this is a cutting tool. This is a cutting tool. This is the cutting edge is just perpendicular to the. You can see that the grid is rounded, and it is it can have little bit of plowing. Okay, it can have a rubbing action because some of the grids can have just a wear plate at the bottom, and some of the grids can be very tough. Cannot just move the material, but it can still allow the material on the two sides. But which is predominant in the removal process is the searing. So the grid has to penetrate to a certain amount of depth, and then with the velocity it will sear out the material. Okay. It never happens to be a orthogonal machining because the tool geometry of the grid is very odd. You know, most material with a negative break angle, and there is a very high specific energy which is involved. Looking at the characteristics of the conventional grinding, you can see first of all the abrasive particles, which are actually the cutting tools. Right? They don't have a specific geometry. If you take a turning operation, if you take a milling operation, all of them do have specific geometries. But if you look at the grinding tools, the abrasive particles, the way it is manufactured, you have literally no control on the geometry. So it's very random. So the rage angle, clearance angles, absolutely you have no control. So most of the time it is negative break angle, clearance angles can be zero, it can be sometimes it can be even towards the negative. So it all creates a problem, and it's lot of it requires a lot of energy to spend for the for the rubbing and the plowing, and essentially a part of that will be the shearing. Now another thing is the random orientation. You have no control. As I said, you don't have a control on the geometry, you also don't have a control on the orientation pattern. You cannot just think, okay, I will place a diamond particle or cement particle on the periphery of a grinding in a specific manner. That's not possible because so far the technology is not supporting that. And of course, this is all essentially leading to the high specific energy because your force per heat is pretty high. At the same time, the velocity of removal is also very high. So since the specific force is very high and the velocity required for grinding is also very high with respect to machining like turning and milling, overall specific energy is very high. And specific energy is very high, obviously the temperature is going to be also very high. So grinding is a very high temperature involved process, right? So if you just see the grinding process, say somebody is grinding steel with an alumina, you can see a lot of sparks are getting generated. Where from these sparks are coming? Because the temperature is very high, the sparks are basically the removed material. Removed material comes out at a high temperature. The moment it is in contact with the atmosphere, it will be an additional exothermic reaction with the presence of oxygen. Then part of the temperature increases and it grows. So that is the reason once you see that you are grinding steel, you can see the spark. If you grind the ceramics, if you grind the ceramics like calcium carbide, you will not see the spark. Temperature is high, but the reaction is not there, which basically pulls up the temperature problem. So now, generally we talk about the grindability whenever we talk about grinding, and you know the typical grindability means how easily you can grind a material. Okay, these things will be repeated whenever we addressing the micro grinding aspects. So grindability indices, the one thing is the G ratio. In case of the turning, milling tools and all those things, we basically talk about tool life, right? Tool life expressed in minutes. Once you take a single point turning tools, you see how gradually it is getting worn down. A particular time it reaches a VB, there's a clamp wear, and you say the tool needs to be discarded. For the grinding, there is no as such rule, but we basically depict the life of the tool by the G ratio, or also the performance of the tool with the help of the G ratio. So you are using a grinding wheel, we see that how much material you are removing, and for that how much volume of the tool is sacrificed. So that is basically volume of the work ground divided by the volume of the work, right? So now if you look at the left side plot, I say the specific energy is as such very high, right? But if you see the material removal rate, if you want to increase, in the grinding it's a finishing operation, but still it is always good you get the finish with the maximum high MRR, maximum MRR, isn't it? So you increase the material removal rate, at the same time you should also get a good finish. So you need to know that what are the parameters which are basically influencing the material removal rate. So if it's a flat surface grinding, so you just imagine a rotary disc is touching with the effective width of part of say B. D is the down pin and BW is the tail pin. So B into B is the cross section which is getting removed, and BW is the table velocity. So altogether this is the material removal rate. This is the tangential force on the disk and the velocity is the cutting velocity. So this is the cutting power. So cutting power by M error, that's the specific energy. The problem is that this FT by this material removal rate in grinding is very high because of the odd geometry of the tool and because the grinding grits are exposed to very little and you have to rotate at very high velocity, otherwise the grit cannot penetrate to a small micron level. It will plunge into the workpiece material. So that is why you need a specific energy. Another example, another way of looking at it I can tell you, say if the grinding is taking place, suddenly if the power goes up, what happens? You can see the wheel will be immediately loaded. There will be loading on the wheel. Why? Because the moment power is off, motor is off, the velocity is dropping down. Velocity drops down means the grit radial penetration is increasing and it will increase to such a height that it is more than its exposed height. So what will happen? Simply the wheel will plunge into the workpiece. That means the wheel will be immediately loaded. So that is the thing. Anyway, so material removal rate you can increase how? You can increase your depth of cut, you can increase also by PW. If you increase the D and PW both, what happens to this equation? You can see VW if you increase, this DE if you increase, this HM is increasing. That means a grit, a small grit is penetrating more. A small grit is almost, if you just imagine it is looks like a little bit of spherical at the tip. If it dips more, it will get a much favorable geometry. The more it is more towards the tip, the geometry is much more odd in the terms of the sharpness of the grit. Right? So it is good that if the grit penetrates more, its specific energy, its energy consumption will be lesser because if the grit penetrates more, it will remove the material much more in the shearing mode rather than the rubbing and ploughing. So what is happening? We increase the depth of cut, we increase the table feet, we increase the error and we reduce the specific energy. But of course, if you increase the table feet, you increase the depth of cut, you may have to compromise the surface finish. So there is a play. You need to really optimize the thing depending on the requirement of the MRR and the finish. Grinding to continue. So over the number of passes, the tool wear or the wheel wear, it's initially the rate is very high. You can see, then it is steady, then it is rapidly very high. What happens in this phenomena at this very beginning, because the wheel topography is little bit random, it has to break even very quickly to come to a stable condition, right? And after that there is a stable grinding. So continuously the grid will be worn out, whole grids will be pulled out from the matrix because the more the grain, the moment the grain is little dull, it has to come out. It will be broken and it will come out, isn't it? So that is what happens. And after that, when the grain is very dull, especially, then what happens? The specific force is so high that it rapidly reduces the, rapidly basically wear out the surface. And surface quality is very important because once we do the grinding, surface quality we have to look into. Surface quality means the surface finish. Surface quality means the surface integrity. Integrity in the sense its metallurgical behavior is retained or not. So your grinding is stable. After grinding also the similar property has to be restored because you are grinding at a high temperature and at the point if the temperature suddenly if you are allowing it to cool down very rapidly, that is subjected to heat treatment. Its microstructure may get changed. And if the microstructure of the workpiece is changed, what will happen? The mechanical property will change. Microstructure is the anatomy of the material, isn't it? So those are the things we need to be very, very careful once we are talking about grinding and the surface quality. Now conventional and super abrasive grinding tools, since we will be talking about the tools, we also need to know how are they specified, right? So if you take a grinding wheel, a conventional grinding wheel, a typical designation is A36 L5P. First one is the grit. So if you have a grinding wheel, it's an alumina. Next is the 36, that's the mesh size. That means if you take 1 inch by 1 inch area, you have 36 strings by 36 strings. And that is defining a square hole. Through that hole, the grains will pass. That means this mesh size increases means definitely the grains are smaller or higher? Smaller, right? So if you want a finer grain, which one domain of the conventional grinding tools. Conventional grinding tools means we talk about only alumina or silicon carbide. But when we talk about super abrasive tools, it's all about the diamond and CBM. You know, there are two things. There, diamond is the hardest material, but in spite of that, diamond cannot be used for many applications. It cannot be used for grinding steel because at that temperature of the grinding, the steel elements, alloying elements, will convert the diamond into the graphite at the contact zone. So although the diamond is very hard, where the diamond is in touch with the steel, those portions will be graphitized, and immediately that will lose the hardness, and that will be all sharp points will be rounded immediately. That is the problem. So you cannot grind any material by the diamond. So steel, if you want to grind with the super abrasives, next choice is the approximately 120 grain size, 120 micron, and there is definitely plus minus because every grain is sieved through a sievage of the same. And then you have concentration, that means how many grains are there per unit volume of the bond and grain together. That is basically expressed in volumetric percentage. Certain volumetric percentage is assigned to be with a value of 100. It's not that the 100 means 100% grains. Certain amount of the certain volume of the grains out of the grid bond and porosity system is designated with 100. Okay, we need to be careful about that. So then next is the B. B is again the different type of the bond system, and other numbers are just like this.
Sir, one query.
Sure, sure.
Just will be this slide. If you compare between the application of alumina and silicon carbide based wheel, the same problem which you have cited for the diamond,
Exactly.
which limits its application to the ferrous material.
Right.
Same logic holds true in case of silicon carbide.
Silicon carbide and
elevated temperature steel has got the affinity towards the carbon.
carbon.
So, what is the probable application of the silicon carbide material?
Silicon carbide is the non-ferrous materials. So all non-ferrous group of materials. So if it is not there, like if you cannot afford the super abrasive tools, like diamond tools is very expensive. If you take a say this is 200 millimeter diameter, so it's an alumina wheel or silicon carbide wheels are how much expensive? Maximum 1000 rupees, 2000 rupees. A very high quality which you might want, maximum it may go up to 3000 rupees, and not on wheel. The same wheel if you take a diamond or CBN, it would be 10,000, 20,000 rupees. If you take even a 400 millimeter diameter grinding wheel diamond, it can be 1 lakh rupees even. Diamond grinding industries do afford because finally you are talking about the finish of the job, so you have to spend money, and technology is also there. So same thing holds correct. So it's all for the non-ferrous group of material. Non-ferrous for the silicon carbide and the ferrous group of material aluminum. Okay, because silicon carbide is harder than the aluminum as such. But this again, which is harder than what in case of the aluminum silicon carbide is very difficult nowadays because a lot of different grades of aluminums are coming. People are developing the aluminum crystals through different routes, and some of the grids are literally very hard. Okay. Anyway, coming back to the micro domain. So when you need micro grinding, so obviously the first thing is the demand. You have a part and you have to create a feature which is of microscopic size. At least one feature, one dimension has to be microscopic in things. What are the applications? So you can see that micro features, many of them, depending on the applications, they are majorly in the biomedical field, electronics field, and optical field. Of course, I'm not telling that it's not there in the aerospace and all those things, they are also there, but currently if you look in the market, the demand is more from these sectors. And kind of component what you need to manufacture is like this. You can see this is a simple medical device. You need to create a small channels as well as small holes. So those are all microscopic dimensions. Here also you can see this is a scanning electron microscopy. You can see this is a 50 micron by 50 micron this unit. But this is just a left out unit. You need a cavity here. This is just a alphabet, nothing else. So there are different things, like different structures, different features you need to create. And interestingly, some of the features you can see are created by the macro tool, but macroscopic in the size. But some of the cases like this, you need a microscopic tool also. Here you can see that this is an insert. On which there are several serrations, several grooves, which are created by large size grinding wheel, but one dimension of the grinding wheel is very thin. So with that you have created the thin slots. So that is a macro size tool for micro size dimensions. But here tool is also very miniature. Tool is also very much microscopic. Let us have to do other applications. So here you can see that small cavity. This is again a medical device. Just to study the effect of the virus, how the virus mobility is there within a small pocket. It's a microscopic volume, small pocket. How to create it on a glass plate. Glass plate, the problem in the thing, the moment you want a microscopic feature on a ceramic or a glass, it is tremendously challenging. It's a metal, still if it is a metal and on that you want to create the micro features, still you can manage with the micro tools like micro milling tools, micro drilling tools, it is possible. The moment I give you tungsten carbide, the moment I give you a silicon wafer, the moment I give you ceramic, it's very, very difficult. You cannot do it with the end mill cutter because end mill cutter itself is a carbide cutter. Right? It can be coated with different type of nitride based coating, then carbide based coating, there can be other coatings also. But as such, the moment you want to manipulate the diamond, these glass plates or the ceramics, you have to have, you have to make some kind of tools, and possibly you don't have any other choice but to make the diamond tools to grind them. And those tools are also would be having a very much microscopic dimensions, overall microscopic dimensions. Here it is the drag administrations, might be a lot of needles would be there, and you just create a pressure through the microscopic holes of the needles. Now the drag will be simply pushed just beneath the skin. It will be almost like painless. Then pH monitoring device, you can see on a glass plate there are several microscopic channels. You just need one drop of blood, it will flow to different things, and you will be having different chemical at different points, and you can just assess the medical diagnosis. Similarly, you can see that cellular analysis. You need different. Basically, you can see this is just to show you the parts which are containing microscopic features. This is a lab on a chip. So a glass plate, you have a lot of microscopic channels, complex contour or a simple contour, either of or might be a combination of that. These are majorly used for diagnostic purposes, medical diagnostic purposes, and some of them are like pregnancy tests, HIV tests, or might be a lot of blood tests, which is just possible. Right? So you need to basically create the micro features. That is the whole objective. On the other side, if you just look into the lenses on the medical equipment or basically optical equipment used in the medical devices, or might be just photographic lenses, optical windows, or the lenses which are used in the laser, they are highly polished, and this polishness of the surface finish, high finish, is there on a complex contour. Right? So they need to be, if you just machine it, you may not get this much good quality of finish. Right? So you may require post machining finishing operation. Sometimes a rigid grinding tool, sometimes a flexible grinding tool. What is flexible grinding tool? Flexible grinding tool, you just imagine that you are making mound for a roti, right? You have the atta, right? And you are just rolling like this. So similarly, if you have a medium which can roll over a surface, that is good. But that medium should be containing diamond or CBN or abrasive particles. That is one way. And another way, that mound, that viscosity of that particular softness, that should be also controllable. So there are different ways. Some people use the magnetic fluid. The magnetic fluid carries the abrasive particle. Now you create a magnetic field around, the viscosity changes, and you can make it like a mound. You can just make it like a fluid. So that can lap over a surface, but that is not a traditional grinding, so-called we are talking about. But many occasions, these complex shapes, it cannot be just created in a normal machines. It all has to be a 3-axis to 5-axis machining center. Once you do that, after that the post thing, you have to do a polishing operation. Sometimes the rigid grinding tool also you can use to make such kind of complex control devices. It can be a lens, it can be a laser systems, or it can be a beam splitter also. So get my point. So two ways, two approaches actually. One approach is that we are making it by the conventional machining. We just go for polishing. It can be conventional or non-conventional lab. Or else I can machine it and I can take a rigid tool and I can just grind over it, right? And everything has to be manipulated, controlling the your CNC axis. These are a few more examples, like micro channel on a sapphire, then silicon micro channels, and these are the channels which are all relating. These are all applications are related to the electronic field. Some more examples, but you can see the materials here. So in some of the cases, as I said, it can be a silicon wafer, it can be soda lime glass. Do you know what is soda lime glass? It's a normal glass, but with certain portion of the sodium oxide within that. Okay? It's a very normal, ordinary glasses, whatever you see. But many occasions you need to create the micro features on that. Here are the dental implants. If you want to put the dental implants, you may have to make the micro drills and might be micro threads. Okay, so that is other attachments can be put along with the crown of the tooth. So there is a crown, and this is the metallic part. You can see that is basically intrigued together, and then entire thing is planted here. So some of the time you need to make microscopic drills. So those kind of things, there's drilling on a ceramic. If you want to make such kind of holes on these things, but generally, they are these particular things are the zirconia things. Mostly they need to have some contour here, but the holes and all those things need to be created on this metallic part. But anyway, their application is very much there. You need to have the small microscopic grinding tool, even to smoothen the top texture of the zirconia after fitting the crown on the tooth. So you can see the application. So this is just the channels how it has been made. Now characteristics. If you come to the microgrinding characteristics, so we need to look at finish of course, because that is the primary purpose. When you are making the microscopic features, obviously the finish is expected to the nanometric level. That is needless to say. Secondly, the form accuracy, very much important. You want to make a rectangular channel. Okay, so that cross section has to be square. If there is an error in the squareness, your purpose will not be served. Although it will be microscopic in nature, but the tolerance on those things will be very tight. That's on the nanoscopic level, nanometric level. So you understand that it is not just the grinding, it is not just the finish. You also need to hold the form, because the form matters a lot to serve the purpose. Then superior surface integrity. You grind things, but the integrity should not be hampered. Integrity in the sense, majorly, there should not be any kind of deviation of the metallurgical aspects. See, your grinding steel, as I said, if it is expected that the surface should be predominantly having an austenitic phase, you should not land up inviting the martensitic phase into that, because that may crack up the material later on. Okay. So similarly on ceramics, if you grind it, you should not invite the invisible subsurface microscopic cracks, which is just nakedly not visible. But if you cut a sample, polish it, you will see that there are a lot of internal microscopic cracks. Or if you expose it to the NDT kind of things, to ultrasounds and all those things, you may see that there will be a lot of microscopic cracks. Those need to be avoided. So they are the surface integrity aspects. Apart from that, as such the material removal is very, very low. That is quite obvious because we are generating the microscopic features. So very low feed is used, and in general depth also is very, very low. Not just because that it is you are basically manipulating a sub-micron level dimension. So now you need to see two things. Say here I was telling one thing. If you increase the depth of cut or table plate, what happens? The grit penetration increases. For that you have a benefit because your more sharper or more favorable geometry is within the material. Correct? But if you grind the ceramics, it is on the other side, because grinding of the ceramic is little tricky because say when you have a material and if I ask you that you analyze the unit volume of material, so you take a small volume, you polish it, what you see under the microscope there are multiple grains, that is the microstructure, right? And every grains would be having the defects inside. When you deform a steel, okay, how the shearing takes place? It is basically plastic deformation. Plastic deformation is realized through the movement of the dislocations, right? But in case of the ceramics, it is not the dislocation movement, it is the cracks which is there or which is under the application of the external stress field. Some more cracks will be generated, they will network and the material will get chip out. But the moment it is a brittle patch, exactly. So if it is a brittle fracture, not a ductile one, so what will happen? The surface, the generation of the surface, the form of the surface which is getting generated by the microscopic tiny grains, you don't have any control on that. Because the cracks will randomly move. But the shear front will not move randomly, it will move according to the stress field. Right? Here the crack will just take its easiest path. So that is why people looked into the things. Can we machine or can we grind the ceramic into the ductile mode? So that means what? Instead of involving multiple number of grains, you have to interact, you have to allow the cutting tool to interact with the work with only few number of grains, maybe just 2 to 3. So in that case, your interaction volume has to be smaller and smaller more. So you should not increase the depth of cut, you should not increase the table width. So depth of cut we are not increasing because the part dimension demands that we should not increase the depth of cut. Okay? But table width I should increase. I want to make a 100 micron channel. 100 micron channel should be made as fast as possible. I cannot increase the depth of cut. Right? But if you increase the table width, what will happen? The grid penetration depth is increasing according to that equation, whatever I just cited at the very beginning. Now what will happen? That will create a problem. So for ceramic grinding, it is just the reverse you have to do. You have to reduce the table width. Downfeed also should be as low as possible and the velocity should be as high as possible. So that the interaction volume comes down and it eventually leads to a shear removal of the material. That is why we say it's a ductile machining of the brittle material. That's a very funny and very interesting concept and very successfully realized. Right? Okay. So here is a video which is exactly a micro milling video. But just imagine that you remove the tool and you replace this tool with a micro grinding tool. So it will be micro grinding. So micro grinding and micro machining, apparently there is not much difference, but microscopically it is widely different, right? Because microscopic, even the micro end-mill cutter or so, there is definitely tool geometry. But for a grinding tool, you know, I have explained to you how the grinding tool looks like. The grids are absolutely random and all those things. But the machine is a similar kind of machine tool you can use. It's not definitely identical, but a similar kind of tools. If you don't have machine, you have a micro grinding tool, you can put it in a machining center, micro machining center, and you can do all sorts of micro contouring. That's possible. Right? You have a 5-axis machining center, micro machining center, you just take a micro grinding tool, instead of the end-mill cutter, you put it there and you do the machining. Or whatever channels you have prepared for the micro grinding, micro milling, you can just make it a better finish, you can accurate the form superior, and that is the way you can do it. And here is another example. This is a micro grinding by the macroscopic grinding tool. So there are two sides of the same coin. This is a company which is Walter. They are very famous in manufacturing the micro machine tools, not machine tools, sorry, cutting tools, which are drills, end-mill cutters, reamers, and all those things. So I can just show you the video because that may be a little more interesting for you. So you know the drill geometry and milling geometry, they are very complicated. And this is how they are grinding. So grinding the main sap diameter, then you have to grind the flutes, and then you have to divide the point angles, or in the case of the end-mill cutters, you have to invite the guards and all those things. So actually currently we are collaborating with a micro tool grinding company. Okay, so they are manufacturing the drills and angle cutters. It's very challenging. The moment you have a cutting tool and what is having a microscopic interaction, especially on transfer carbide and all, your machine tool, your CNC access control and everything can give you good attempt to make the form, but there is no guarantee that you will land up with those kind of form because they tend to chip off all these cutting edges. So currently we are working on a problem how to reduce this chip off. So you need to understand the metallurgy because chipping off is not only just a cutting tool and it's not only just a cutting mechanics related problem. It is very complicated problem, which involves also the materials aspects a lot, and of course design, thermal, everything comes together. So now I was just talking about the micro grinding. So especially in the micro grinding, what happens? There are two aspects. If you machine the ductile materials, and in that case your micro grinding features, which is the very small depth of cut, table fit of course it is at your hand, and very high velocity. Altogether what happens? The grid penetration depth is low, and specific energy consumption increases. So for conventional grinding to micro grinding, the problem is that the grinding grids, they interact with a smaller volume, and for ductile material that's a problem. But for ceramic materials, if you increase the high velocity, you have an advantage. That means you can machine the ceramics in the ductile mode. Now if you compare these things, this is typically the grain size, as you can see, it can be as small as 12,000 mesh size. The average grain size, it comes down from 200 to 12,000 mesh size. So it's very, very fine, almost like a talc. It's a powder. Temperature, of course, is 100 degrees centigrade in micro grinding because your deformation volume is very, very low. Right? So this is what happens and how a cutting tool interacts with the multiple grains. There are the defects in the grains and how the dislocation moves. Okay? But again, I'm repeating you, for the ceramics, it should be as low as possible, the number of the grains which is interacting with the cutting tools. So this is, I was explaining you that why you need the ductile mode machining. If you don't do the ductile mode machining, that means if you use a table fit little higher or a down fit little bit higher, what happens? The grid will penetrate more. And if it penetrates more, you can see beyond a point, it will start cracking the material inside. So there will be defect inside. So this is a single grid test. If you take a disc, if you just join a particle, abrasive particle, you allow it to machine, what will happen? It will make a scratch. The scratch will start here from a zero depth. It will take the maximum depth at the end. Okay? In this path, after a certain point, after a certain critical distance, you can see there will be a microscopic cracks. They are getting generated in the ceramic material, so which is not at all favorable. So that is why you need to grind these things in a ductile region. That means your grid penetration, maximum grid penetration depth should not cross this much value. So you have to just restrict yourself within this particular domain. Okay, so this critical depth of cut can be also found out. There is a typical very famous Befan's equation. This is E by H, your modulus by hardness, and fracture toughness divided by the hardness. Right? So this is the typical brittle fracture which is reduced if the grid penetration depth crosses that particular point. So is that clear to all of you? So ductile mode machining and the ductile mode machining of the ceramic material. Did you get my point?
The deformation in the brittle material also is done by the dislocation movement restriction of the plastic.
Yeah, see the thing is, as long as it is confined within the two grains, we tend to do that. We want to do that because it is not the cracks which is propagating. So we tend to, but you see that whatever defects are there, we just need to manipulate it within a very small volume.
It is the grain that defects we.
Yeah. So basically, if there is a grain which is not having any defect, so it is literally difficult to see some of the set of the atoms out of it. So you have to have the defect. So that defect is actually, defect is not good, but defect is good in terms of the machining. You need some amount of defect in the material within the few grains. Right? So, okay.
Sir, one question.
Yeah.
As far as our conventional cutting is concerned, we favor tool having the positive rate. But since in this particular case, in case of grinding,
We don't have any
we
control.
have a positive rate. So
Right.
high negative rate will have to be some negative consequences on the cost.
Right. So that is always there.
That is
So,
also
yeah.
true in case of
So it is something like that. You have a naughty student in the class. You have to accept him. So you have to accept him, but you have to get the work done by them. So it is exactly the same thing. That naughty grid has to work. How I can do it? I increase the velocity. At the increase the velocity for ductile material, the material will get little softened. So the negative impact of the negative break will be little less. So you are machining a hard material, and if the material becomes little soft, what will happen? Material will give lesser resistance, right? So the effect of the negative break angle just get to some extent, to some extent reduced, but you cannot eliminate. So it is like getting the job done with a naughty student. I should not say bad student because everyone is good in the class. So yeah. So
This equation is find out through experimental analytic.
this is analytical. This is analytical, but this coefficient is to some extent matched with some experimental data. This is a very far more written in the 70s. This equation was born much before the birth of me. So, but this is a very famous equation to find out what is the critical depth the grid has to penetrate. Like it has to be lesser than that. Your grid penetration depth has to be lesser than this critical depth. Now the most interesting part is the grinding to fabrication. We learned about the little bit of fundamental topic, how the removal takes place, specific energies, parameters, and all those things. But now you need to make the tools. No, we talked about the macroscopic, larger size tools and the microscopic feature. But now we'll be exclusively talking about the microscopic tools and making the microscopic features. Right? That's pretty interesting. Now let us imagine that this particular tool is just a 500 micron, 400 micron tool. So this tool must be having abrasives at the tip. In case of conventional tool, you have just a carbide and then you machine it. But here you have to make the carbide rod and then you have to add the abrasive particle at the tip. So it's a secondary problem you are basically adding on, right? So now for that, there are several steps actually and several components involved in the making of the grinding tools. First of all, the tool sank material. So tool sank material, if it is a very small diameter tool, can you really manage it with a medium carbon steel? You cannot, because the E value is so low that the flexural rigidity will be very low. So you know the bending, no? The moment there will be a grinding or machining, there will be a load. That load is just acting on the tip of it, which is just like a cantilever. There will be deflection. This deflection is kind of connected to the. Say if you just take a cantilever beam, it is PL cubed by 3 no? 3 into EI. So E has to be low, I also has to be low. But you have very much unfavorable things in terms of the E. So that Young's modulus, that particular thing has to be very high of the material. So basically flexural rigidity needs to be very high. Because of that, for that reason, you need to choose symmetric carbides like tungsten carbide or even can be a ceramic tool. Okay, then how to make them? So the substrate on which the abrasive particle will be joined, making them itself is very challenging. How can we make a small carbide rod from a little larger rod? Of course, they are mostly powder bed energy product. You get an approximate cylinder and after that you have to do the turning. But turning itself is a very complex, problematic because it's a conventional process. You use a turning tool and there will be geometry and during the process there will be force and that can basically make a tool which is not straight, which may not be a cylinder. So you have to make here a cylindrical tool. So there are challenges in the mechanical machining, but we can take the help of hybrid machining like where electrolysis grinding, or otherwise we can just do the turning or followed by grinding or just grinding alone. I have shown you an image that Walter company who are producing the grinding tool, sorry, not grinding tool, milling tool and the drilling tool. They are grinding the carbide sands directly by the diamond tools. Since you are grinding carbide, you have to use the diamond tools. So all are in a CNC machine with the programs. You make the flutes, you make the point angles, all those things. Okay, but here we don't want the complicated features, but we want to just make it. So you can just do the grinding and you can make a 500 micron rod very comfortably. But if you come to the domain of 100 micron, or if you want to go below that, just want to make a rod of 50 micron, it becomes very challenging, very challenging, right? So anyway, then the addition materials are diamond and CBN essentially because most of the time we are basically manipulating the ceramics. So diamond has to be used, CBN has to be used, superabrasives are the only solutions. Ceramics, diamond and hardened steels, it is all CBN. Then the bonding type, how you are going to join them, that's the most challenging one, right? So in normal grinding, it's a large size, you can have vitrified bond, resin bond, metal bond, whatnot. But here, joining the superabrasives on the periphery of 100 micron diameter thing is very challenging. And only few options are there left out. One is like electroplating, you have electrolase plating, you have gold spray, and finally there is a current trend of making things by the brazing technology, right? And which binders you use? You can use a nickel-based binder, you can have a cobalt-based binder. After making the tools also, you may need some post manufacturing processes to make those micro tools, right? We'll come back to that, and that will be really interesting. So everywhere, if you just look at it really critically, we will come to the very fundamental understanding of the fundamental science of machining. Without that, the technology cannot be advanced. It's very difficult. Let us just take that micro turning. If you want to make a rod, say let us just make it like a hardened steel, okay? And you use the CBN tip tool. You want to just turn it. What are the possible causes? This can get bent. Why? Because there can be a possibility of high amount of radial force. Now the question is that this radial force, how can you reduce it? To get the answer, we have to get to the multi-factor diagram. So that is why I am telling that everything is connected so much to the basics of basic understanding. I think since many students are there, I will tell you, you people just take a thinking, okay, what is there in engineering? I'll go and join in a company, they will train me up and I will just do that. That is management. If you want to develop something, you have to, everything comes from the ABCD. Unless and until you are thorough about the ABCD, it is not possible to learn. So it is a very gross and very wrong notion that, okay, what is there is, nothing is going to be useful in the industry. Nothing is going to be useful in the industry if you are joining in a marketing job. If you are taking up a marketing job, if you are taking up a financial job, if you are going to take up just a managerial position, that's fine. But if you have a higher ambition, if you want to develop something on your own, everything is deeply rooted to the very fundamental understandings of physics, chemistry and mathematics. The people are not so casual who are sitting on the board and sitting at syllabus for the physics, chemistry, mathematics in the 10+2 level or even in an engineering level. It is not like that. People are thinking, people deeply thinking and formulating this, all this syllabi. So never overlook this kind of things and they will never misguide your juniors. That's my sincere suggestion. Okay, that is, I have seen personally, people used to tell what is there. But now today, when I am doing research, I am just trying to compete with the most advanced labs of the world. I see these are the understanding which is necessary, which is essential. Without that, you cannot just move an inch forward. Okay, so be very careful and pass on that message to your juniors. So if you really want to take up a career in the development phase, even in an industry, if you are new technology someone is adopting, you need to understand the technology. Otherwise, today that technology, tomorrow what you are going to do? Another technology will come and you have to buy. And you are buying everything to the, you are giving your money all to the foreign countries and you are reducing your foreign reserve foreign currency. That's very bad. Even if you take a technology, learn it, you need to develop it further. That is how the companies are coming. If you just look at TVS, they tied up with a foreign company, that's a Japanese company, and then they became on their own. Now, if they want to sustain the next 10 years, they have to have their own R&D. They need to understand all these fundamental things and they have to develop. Unless and until they take it further, you cannot do. You can manage if you are happy with just 30,000, 40,000 or 70,000 salary in the pocket. That's a different thing. But I'm talking about something that responsibility should be there on our shoulder because we have to take our nation ahead. It's not for big talks. We have to do it for our next generation. If we don't do that, we are happy. We can just manage. We can just live a very mustful life. But what will happen to our next generation? We are questionable to them. Right? Anyway, so coming back to these things, if you look into the equation from the Marxist circle diagram, there is a cos phi component, right? So if you have how much would be the radial component? That is a pxy cos phi. Thrust force into the cos phi component. So if your phi is 90 degree, you are the beneficiary. So that means all these tools should be there with the 90 degree phi angle. That's an approach angle. Principal cutting edge angle should be 90 degrees, right? And if you have a nose radius, what will happen? If you have a nose radius, that will induce some amount of value of the phi. That will basically drag the chip. That will induce some amount of the radial stress. That will have some component of the phi. 90 degree will be reduced, isn't it? So that is why the phi has to be negative. The nose radius should not be there. It should be as low as possible. But there has to be nose radius. Otherwise, the thing will be broken. So nose radius should be there, but it should not be that much. And then that is the way you need to machine it. Only then you can avoid the lateral radial force and you can only have predominant longitudinal cutting force. Then your form accuracy of this shaft, the microscopic 100 micron shaft will be retained. Otherwise not possible. Right? And after that you may just go for a grinding to just make the things more and more accurate. You can do the micro EDM. Like you have a disc which is just this is the tool and you will be having a dielectric. This disc will be rotating and the spark will be generated between this carbide rod and the disc, which is also conductive material. And it will be continuously, it will be rotating, this will be also rotating and it will go up and down, or this will go up and down. So that the finish will be created there. This is mostly, I can say this is not yet industrially practiced one. Okay, this is just in the form of the research till now, but it is quite advanced at this stage. People are getting good finish. Earlier there was an issue with the finish. Now they have also got rid of it. Okay, so this is like a single wear is a problem many officers because single wear is a point. It is like a turning, no? So you have a single wear and you have a rod. You have the dielectric fluid. You exercise the EDM operation. The spark will be generated. The material will be removed, and that is the way if you move it. It is like a helical movement, just like a solid cutting tool. But what will happen here? The control of the crater is not very much smooth. So instead of single wear, you will use this kind of thing, so that it is not a one-point spark. It is a multi-point spark and overlapping spark. So because this will be moving over this particular weight, and this will smoothen out the entire cylinder, right? So that is the way we can basically do the micro EDM also. Micro EDM in the sense we are just producing micro part. The tool of the EDM, that is microscopy. Now you see, you can also join the CVN on the diamond by the electroplating technology, right? You have electroplating bath, typical galvanization process. You have a nickel solution. Nickel will be dissociated and you dip your tool, put a negative potential to that. So nickel plus will come and get attached to it. And this tool will be just, it will be dipped inside a jar, which is already packed with the diamond particles or the CBN particles. Okay, you have a beaker. Within that, you just dip it. The beaker is perforated. It is perforated in such a way that the grits will not come out, but the nickel ions from the surrounding solution it can go in. So it will build up slowly, and one layer of abrasive particle will be joined. That is called a single layer configuration. But micro tools are okay with the single layer configuration because you don't have to go for very high amount of removal rate. Okay, so the wear on the tool is very less as such. So one layer configuration is good enough. There is another thing which is electrolace plating. Electrolace plating is absolutely a chemical based one. So similarly you have I will come back to that later on. Another thing is cold spray. You can do the brazing. People can also do by the coating methodology. That's pretty unique technologies. What I first you grind the, this is a small micro tool which is just manufactured by this a rotary grinding tool. It just makes the problem. Particles are embedded here, right? So with that you can create a micro channels, and this is the group. This is a very famous group. Professor Orish is in a German university, and this is a micro channel which is just cut. Okay, how much is the width? You can just figure it out from the scale curve. Anyways, so if you magnify it, you can see the some percentage of the grid height is basically embedded. But this is a mechanical joint. Electroplating is a mechanical joint because you have, see, this is a carbide rod, and on that you have a 100 micron particle. Nickel is embedding on it. So 100 micron will be just surrounding that. There will be a pile up of the nickel, so that it cannot come out. So it's a mechanical joint. So the joint strength is not very good. So the moment you want to machine ceramics with this kind of tools, the grid tends to get pulled out. That's the only problem with this. Secondly, you can see that some of the applications, as I said, that you see the machine tool bed, it is just like a normal CNC machines, tabletop CNC machines, and but integrated with a very high speed spindle. As I said, for ceramic grinding or normal grinding, your high spindle speed has to be very, very high. If the grinding velocity has to be very high and your diameter is very low, what happens? How can you manage that? You can only manage that by increasing the RPM of the cut. Right? So in normal grinding, you rotate the disc by 4000, 5000 RPM. In this case, it has to be 1 lakh RPM because your diameter of the cutter is 500 micron and the grain size is just 30-40 micron, or it can be even less than that. So interesting and fascinating here. And here, after that, you can see that you have machined the carbide, but there is very soft cutting. You can see the edges. If you just magnify this edge, you can see this soft cutting. There is no dislodgement of the carbide particle. There is no extra bulging of the material. There is no chipping of the cutting edge. Okay, so this is by controlling the parameter and of course high speed and the rigidity of the machine tool, but matters a lot. Now coming back to another example, that is the machining of a silicon wafer, single crystal silicon, and that need to be contoured. And you know the tools are here. This is just an example. People, many occasions, what they do, they even take machining centers and they remove the spindle and they retrofit a high speed spindle. But the micro grinding operation demands much more than that, you know, because yeah. So micro grinding features micro grinding demands much more than that, because you need the rigidity of the machine tool. You need a good control on the spindle side. I will come back to that again. So now you can see that tooltip is just an example. You can see the operating parameters. See here the feed rate is millimeter per minute, 2 millimeter per minute, 3 millimeter per minute, 10 millimeter per minute. So low. In a normal grinding, this is in meter per minute. That's 3 meter per minute. The same values comes in the order of meter per minute. So it is 1000, 1 by 1000. So that much fraction, that much slow. Because otherwise you cannot grind the ceramic. It will simply induce crack. Okay, and it needs to be avoided. So microwave chipping needs to be avoided, and people made a electroplated diamond tool effectively used by controlling the parameters so that the chipping can be grossly reduced. But again, you have a point beyond that you cannot do, the chipping is inevitable. For that you have to do further modification of the technology. So this is what happens during the grinding depth, surface roughness increases, and with more number of passes also the surface roughness increases, because what happens with more number of passes, the grinding tool tends to get worn down little bit, because if you are especially grinding the ceramics, the grids tends to get dislodged, grids tends to get fractured, grids also tend to get tertiary wear. So because of that, your overlapping cuts, because if you have lesser number of grains per unit area, your overlapping cuts will be much more less, and for that you will be having a compromise on the finish. Now you can see that it's a setup. People say that it's a nano grinding setup developed by this Professor Arish and his team. It has been published in the CIRP annals. Just look at the feature of the machine tool. You have grinding tool here, you have microvarium facility, you have galvanic module facility, and you have grinding facility also. Why it is so? There must be a reason behind it. Say, if you use such kind of machine tools, what is the problem? First of all, the machine rigidity is not meant for grinding accuracy, number one. Number two, the spindle runout may not be acceptable. Number three, this is made for machining centers. So every occasion what you have to do, you may have to take out the tool, it will go, it has to take another tool, something like that. So here also during the grinding, if you want to change the tool, you have to take out the tool, you have to put another tool, something like that. But see, this grinding tool, whatever you are going to fix it here, it was made somewhere else. You take it out and you fix it in the college here. So the moment it is in a machine, there it shows almost like a very close to nanometric level accuracy in the eccentricity, the runout. If you talk about the geometric dimensioning, right? But if you take out the same tool and fix it in the micromachining center, you can see this is a 5 micron runout. And that 5 micron runout, if you rotate it at 1 lakh RPM, it would be a dynamic eccentricity in the order of 20 micron. And don't expect a micromachining or micro grinding with the help of that. So in the machine's bed itself, you can make the tool, and then there itself you grind on a separate platform. So this is a larger platform and it's a multi-stage operation. So here the micro-VDM module, this carbide rod will be plated, and that plated tool will come here, it will grind your surface. So there is no loss of accuracy in terms of the eccentricity, and the tool life will be enormous, the surface quality will be very high, and you can hold the form much better. So that is why it is a nano grinding center. One center you have everything, and the structure is also very different with respect to the normal machining center, because this kind of machine tool can offer very high rigidity. It's a very high precision. These are the micro tools, micro group with a tool diameter 4 micron. So 4 micron tool, you cannot just make it on a different platform, take it here, put it and you will grind. Just imagine 4 micron. How much is the micron level diameter of your hair? So 4 micron tool, but it's a rigid tool because it's a constant carbide, right? And with that you have to machine it. Why you need a rigid tool, that also will come. So finally what happens, you can see that with that is machining micro groups and quite effectively. Now look at the surface finish. If your material removal rate, total amount of material removal is higher, obviously surface finish is going to be little higher. That is because you are increasing the table feet. Table feet means your grinding groups will be little deeper. Because of that, your surface roughness basically shoots up. So this is what is happening, and range 2, this is a grain size 1 and grain size 2. So 1 micron grain, 2 micron grain, larger grain and smaller grain. This is again the same thing. You know the finer grains produces a better finish. Why does it so? Because finer grain means per unit area of the tool you have more number of cutting points. It will create more overlapping scratches. So you give some good finish. So this is an amazing world actually. Then this is another approach. People try to make even a cheaper approach, like how to make the tools. This is a cold spraying tool. So let us just look into the past schematic. So it is like an abrasive jet machining. You have the abrasive which is basically carried by the carrier gas at a very high pressure. So if you increase the pressure to 70 bar, this 70 bar pressure will just trap it will just exchange the momentum with the faint microscopic particles then they will flow together and they will impinge on the surface, substrate. This substrate is your connecting substrate. Okay? These grains it is supposed not to machine. It is supposed to go hit and get embedded. So you need to, the process is similar to the abrasive jet machining, but it is not machining, it is abrasive jet embedment. Okay, so the velocity has to be controlled in such a way that the abrasive particle will be flown away and it will just heat and get embedded there. So this is one group, they just tried it that widely gone, and they have attempted these things on ceramic tools. Okay. So this is the pencil type microtubes, and the pencil type microtubes are needed because here it's a small diameter, it's a large diameter. Large diameter to be held in a bullet. It's a small diameter which will be operating. We cannot have a step, so you have to taper it out. That's a design principle, right? And here in the tip, you cold spray the things and it can get embedded. But this is not a very successful technique. It is not industrialized, but people made an attempt and people have shown that okay, this is also a possible way of making the tools, which is a very cheap way of making the tool. So sometimes whatever you just need the microscopic contours. May not be that much bothered about this form and all those things. It may happen, okay? But suddenly when your precision level requirement is very, very high, this tool is not suitable because you can see after some amount of grinding, the grids are getting dislodged, right? And again, you can see the VW is micrometer per second, so 300 micrometer, that is 0.3 millimeter per second, very low, and velocity is 4 meter per second because it's 4 meter per second means it is not also very high, right? So it's quite low. So this is how the things are. So other than that, roughness and surface roughness with respect to the feed rate and spindle speed. So spindle speed, generally what happens if you increase the spindle speed, the cutting is more finer because grit penetration depth is smaller. But if you increase the speed too much, then there is a runout problem. The dynamic eccentricity of the tool increases. That makes the problem. Okay, so your surface roughness tends to increase. Feed rate is bound to increase because if the moment you increase the feed rate, the scratches would be deeper. Yeah. So this is another technique which is electroless plating. I don't know whether you know about this process or not. Electroless plating, there is no question of any kind of potential difference between the electrodes. You don't have to use any electrodes. It's like you take a beaker and on that you have a chemical solution and that solution would be suspending the diamond grids of the bearings. And here in between you have the substrate dipped into this and it will be rotated. There will be chemical decomposition which will take place here. And again the nickel is basically taken out from here. So essentially you need a nickel based salt. You can use nickel sulfate. People have used nickel sulfate here. And then they use some I think that is sodium hypophosphate. Okay, so the nickel ion will be just dissociated in the solution, and initially this particular substrate is coated with nickel. Because if you don't coat it with the nickel, this will not be chemically active. The moment you coat with the nickel and you dip into a solution which is having nickel sulfate in the presence of a reducing element which is a sodium hypophosphate, then the nickel will come and it will get the electrons from the surface of your and it will get deposited. So it's you don't have to use any kind of current or potential difference between. You don't have to use the electrodes. So it's a very simple way of making the tools. So simple way means definitely the cheaper. So this is how it is done. One nickel layer and on that slowly the nickel layer will build and it will embed the lattice particles. Right? So this is how the things are done. So if you allow the rotation for a long time, 60 seconds to 75 seconds to more and more time, so definitely the grids are getting embedded. Taken majority of the grids below the within its coating. So it is not definitely one type, so which is desirable is this one. So a little nice distribution and reasonable exposure. Similarly, if your rotational speed is very small, then the collection of the grains around it is reasonable, but if you increase it, it is better. But if you increase it further, then it cannot even come, and because it has to also take some time for getting deposited on the chemically reactive surface. Okay. Then we talk about the micro grinding tool here, their applications. So let us just see this. This is a very interesting tool. So now we are talking about the bonds. We have a substrate. So everywhere you can see that we have a substrate and we make the substrate. We make all these substrates, and on that we embed the abrasives, either by the electroplating or by the electrolysis coating or by impeachment cold spray. But you can do in a different way. That is, you can simply first get this substrate, this tool substrate coated by a CVD, diamond CVD. CVD process is well known, and you can make a diamond coating on a tool. Diamond coated tools are available, which are exclusively used for machining aluminum and aluminum based materials. It can be aluminum based alloys, it can be aluminum based composites also. So those things are done by the CVD coated tool, but that purpose of the coating is to make the coated tool, the tool chemically inert to aluminum, so that the beta base does not form or the wear is low. But here what we do, we take the same diamond CVD coating, thick coating, might be 20 micron, 30 micron coating. Then what we do, we ablate the coating with the laser and to create the geometry of the tool. So what will happen now, the same coating will be there with the definitive tool geometry. Is it not a better choice? Because otherwise your diamond particles, CVD particles don't have any kind of definitive tool geometry. But in this particular case, you are texturing a coating, and you are texturing in such a way that every segment of the cut portion becomes a cutting tool. Okay, so that will be having a definitive tool geometry. Now with that, machining is much better, grinding is much better, because now that question of high specific energy is not coming into the picture at all. Okay, not only that, say you just imagine a tool. Abrasive particles are supposed to get into the action. But what about the radial distance of those all grid points from its axis? From the axis of the tool, the radial distance of the all grid points, grid tips are the same? They are not same. They are different. So that means if you want to use this tool with just a 3 micron, 4 micron depth of bar, it is problematic. You cannot grind. You cannot grind means all the grids will not participate properly. Some of the grids will not participate, they will remain inactive. So you need to reduce it. For that, it is literally very difficult to grade all the grains of the similar size and maintain the radial height to be same. So two solutions. One, you can make the tools, then you need to condition the grade tips. You can do it by the laser tracing, you can do it by the mechanical tracing also. That can be done. Otherwise, this is the solution. If you just get a coating on the surface, what is the advantage? The coating is very smooth, 10 micron all around. The tool is 500 micron or 200 micron, you have additional 20 micron concentric cylinder sitting over the substrate. Now you texture it. So all radial points that way you are creating, they are all having an equal distance from the axis. So now when you want to use that particular tool for the grinding, all the points will cut in a similar fashion. So you get a very good finish, and performance of the tool will be very, very high. So that is why you can make a CVD tools, and of course you need to also control the parameters, because CVD tools are also texture, roughing texture, a little bit of ups and downs. That surface roughness, it can go up to 1.9 micron. Okay, but you need to reduce that particular thing to urgent value of 33 nanometer. That is possible by controlling the parameter. Okay, so this is the interesting part of it. So then people made the tool and CVD coating, and then after that they ablated by the laser. Now it is wonderful. You can see this is the cutting tool, and it can cut so smooth. It can give a fantastic surface finish and with very high level of surface integrity. Because the temperature would be less, force should be less, power consumption would be less, everything would be less. But on the other side, electroplated tools, you can see they will be tending towards the grid pull out, all the grids will not participate, lot of other problems will be there. Right? So this is how the things are done, and if you use a like a plated tool, let's say just a test after say 960 passes, almost 1000 passes, with an electroplated tool, you can get a RA value of 1.09 micron. Whereas if you use a CVD coated tool, texture one, you can get an RA value of 0.60. That means just 630 nanometer. That's a wonderful achievement. Now, what are the challenges? So overall, we talk about the glorious part of it, but in spite of that, just 1 second. What are the challenges we need to know? First of all, low feed rate. Then I explained why the low feed rate is necessary. The crack propagation sometimes is very abnormal, if it is especially for ceramic grinding. How to get rid of it? Perhaps if we can induce hybrid machining, or we can have some adaptive or assistive technology along with that. Secondly, the machine constants is also there. We can have high speed spindle with minimum deviation because spindle runout has to be very low. Then high machine vibration should be avoided. Manual cutting speed from spindle axis to the tool bed, that is another technology which is essential. Are you getting closer to your lunchtime? So this is one, and another thing is the moment we talk about the very finer grains and all, we can sometimes getting handicapped. They are rubbing at the say that the cutting velocity is 0. So how to manage it? So there will be some kind of rubbing and plug at the center. So the surface quality at the center level that can get damaged. So for that, there can be some solution that we can also talk about. And another thing is that you need to have a dedicated machine tool. So you need to have a special purpose cutting tool. You need to have a special purpose machine tool, and also you need to have several improvisation of the technique itself. So what are these? So first of all, so sometimes if you do an ECDM process, electrochemical distress machining, you can make a microscopic feature like this. But you can see the form is not accurate. So it has to be assisted with the second step process with the grinding. The grinding with a textured PCB tool, then that will incorporate the micro grinding and that will make the form more and more accurate. So just a non-traditional approach ECDM may not be sufficient. Okay, but ECDM alone, if you do alone the micro grinding, it may take time, it can hamper the integrity. But the ultimate form can be just restored with the help of a. They have done it, but finally they again process that particular channel with the micro tool, and you get a very fantastic finish. Okay. Right. Now you can see here the chemical surface modification and micro grinding. Right. So this is another thing. So you have a silicon wafer. You want to grind. What will happen? It tends to chip off from the side. So what you can do, you can put a micro layer. This is not micro layer, sorry. This is a sacrificial layer. You can put it on some amount of thickness. Might be a few hundreds of micrometer, or might be just a few millimeter, 1 millimeter or 2 millimeter. Then you can keep on grinding. So what will happen in that case? The chipping and all those things can be. This side there is no sacrificial layer. When the tool keep on moving, the grinding operation was performed slowly. Then you can see the chipping could be arrested on the side where there was a sacrificial layer. So this is basically just to arrest either the chipping or the bulging of the material. This is important for ceramic to avoid the chipping. It is important to avoid the bulging for the ductile material. So this is how it is done. So what we do, we take a silicon wafer or whatever it is, we just put a sacrificial layer, which will get settled, get cured, it will become hard. then you do the micro grinding. So then at the end you can avoid the micro chipping which is happening here without the presence of the second machine layer. Okay, this is one good solution. So this is several steps of different RPM and different table speed. Now machine tool, as I said, is very important because high spindle rotational speed should be there, and it's all about 1 lakh or above. So these spindle designs are very special. Their alignment has to be very special. Their perpendicularity setting, rigidity, and all those things has to be quite compatible to the requirement whatever is necessary for precision jobs. Low runout of the spindle runout itself should be well within 1 micron or even less than that. Well within 1 micron, anyway, that means less than 1 micron. High positional accuracy of the machine tool, because wherever you want to make the hole or wherever you want to make the channel, the location with the help of the CNC machine tables, the positional accuracy should be also ensured. Then noise and machine vibration, that should be bare minimum. So you have to use concrete beds, other vibration absorption mediums. The design should be such that the fluctuation of the force can be absorbed and it will not propagate much to the machining zone. Low reclamping errors, then reduction of the overall cycle time. Those are the normal part of it. And of course, if possible, if you can make a machine tool center or the machining center, nano grinding center, where you can make the substrate, make the diamond or the CBN embedment, and there itself you machine it. Then the accuracy level is the maximum. But they are very special purpose machine tools because the cost of the tools would be few tens of crores. It cannot, because it's a combination of several steps. But one thing, as I said, that when you are making a contour grinding or might be even a slot grinding, especially a contour grinding, slot grinding the scope is not much. But the problem is at the center. This is rotating at the center, the speed is 0. So the shearing or the removal of the material by the shearing is very difficult at the center. So what is done? The moment the tool is coming back, coming to this particular orientation, the machine understands and immediately it will make a tilt, and it will adjust the tool in such a way that it will be inclined. Like instead of doing it, it would be like immediately it will incline and touch the surface. So you get a velocity to grind. So this is called a adaptive or adaptive spindle axis. Depending on the situation, the spindle axis will rotate and then it will grind. On the same path it will grind, but it will just little incline, so that you get a surface speed. That's a wonderful idea, but so far no commercial machines. They are all in the lab, but in the process of the making. So I think with that we are very close to, or should I continue, sir?
It's already 12 past 5 and you are continuing for the last 1 hour 40 minutes unjamming reverse.
So time process, so yeah. So I can conclude.
Okay. So I have 2-3 queries, not
Sure.
exactly specifically related to the micro handling because I don't have that much of exposure. So as a part of, since I take up the road of teaching CNC machining, so I have to some extent keen interest about the cutting tool area. As regard to the fundamental basic alumina wheel, how zirconium toughened alumina can be developed, or what is the procedure?
Professor Jana, I think those things are all related or linked to the single point turning tools, not to the grinding grades. If you see the zirconia toughened alumina, your alumina as such, since it's a ceramic material, it needs to be toughened. And many times they put a zirconia toughened, sometimes they put silver toughening, and that especially what happens that cutting edge chipping can be arrested to a greater extent to that. But that kind of toughening within the small grains, I am not much sure about whether the industry is taking up. But people are using different kind of methodology like sol gel methods and all those things to produce different types of alumina grains. Okay, so those grains are relatively having much more better engineered value in terms of the hardness and toughness. But certainly they can be done, but whether they can finally come in the form of a grain or not, I'm not sure, because I don't think that QB and Nano they are making such kind of abrasives. but they can definitely, they're using some tapping mechanism which they are not revealing. Because just right now, QB sent me some samples on the alumina grains. They claim that they are produced by the Soldier method. They are more tough, and they are asking me to taste it in a typical grinding. How does it crack? How does it fracture? So that they can use it for the conventional tools. So definitely that can be toughened, because say grinding is not just the hardness of the tool; it also needs to be tough because it is impacting on a very high velocity. Hardness is necessary because it has to dig, or I can say it has to penetrate, and then it has to shear. But this is a soft load kind of thing. It loads, then it just zero load again comes back, loads builds up. So it's a fatigue kind of things. And for that the toughness is necessary, but they have different routes. They during the seeding of the alumina, when they grow the alumina crystals, generally what they do, they grow the alumina crystals or silicon carbide crystals, then they break it, and then they seed it according to the different sizes. So during this building process, they use lots of tapping mechanism. Professor, you are absolutely correct, but they are very common in single point tool or even the other tool, especially inserts, making the inserts for milling cutter or turning inserts. They are very common, but for grinding, I am not very sure whether people are doing it. Yeah. So.
And as regard to the single point CBN tools, what will be the sizes? Because it cannot be that much bigger as compared to your standard tungsten carbide insert or ceramic insert.
No, can you please repeat your question? Single point CBN means?
Cubic boron-nite.
CBN, what type?
It is very hard and of course costly and difficult to manufacture.
My point is that you are referring to turning tool.
Turning.
Okay, so CBN turning tools is CBN. There are two things. One is polycrystalline CBN, and another is a single crystal. That kind of thing, which is very hard and tough. So those kind of things, they make it into small pieces, and they place in front of the tungsten carbide inserts.
The initial processing is similar to the powder metallurgy or specially?
No, CBN is developed in the lab. They make the CBN and the high pressure temperature, that kind of thing. So typically the diamond is made in that way. CBN is also basically it's a chemical synthesis process. They make it, they grow the crystals, and they can also use the high pressure high temperature technology to convert the HBN to the CBN. So CBN and diamond, they produce in a typical manner. They just allow the crystals to grow and come to a particular size, small size. And those things are almost predefined. Then they do some polishing and all those things. Then they bring it, they braze it in front of the tungsten carbide insert, and then after they grind it, because you cannot match it exactly. So there will be a little bit of plus minus. So after joining them, you need to just grind it according to the geometry. So otherwise, it is that the small pieces of triangular shapes, square shapes, they are produced in the lab itself. Then you need to braze them. PCBN things are solid things they make in the lab itself by the that is a powder PCBN especially, because that they use the binder in that.
And my last query, as regard to your this sophisticated micro grinding, what will be the special requirement regarding cooling?
So cooling, of course not the flat cooling, because flat cooling has a velocity which will have an impact on the cutting tool. It has a pressure also. So the best option is like that. Best option is the dry grinding if you can do, because most of the these kind of tools are metal bonded. Diamond is also good. Your temperature generation is also very low. So exclusively it can be green cutting fluid, zero cutting fluid grinding. But at all, if something to be used, the next choice is the air, cooled air, chilled air at a very low velocity. And the third choice is the minimum quantity lubrication. That is the current trend which is going on. Many industries have adopted, especially Ford. Ford was having an industry in Chennai. Now they closed it very recently. They are using all the MQL setups in all their machines. So MQL is not just a gimmick; it's the reality. Because it can. Please sit down and please ask the question. I'll be happy to
For
answer.
single point micro cutting tool, then what should be the development of cutting supply of cutting fluid for single point?
I didn't get it.
For single point micro tool.
The single point micro tools, whenever you talk about, they are as such they are macro tools, but having a very microscopic tip. Microscopic field in the sense the radius is very short, radius is not there. So if you see you do the micro turning with an insert, they are all with a macroscopic insert. But their tip is very sharp and they don't use this approach angle, that principal cutting edge angle is kept as 90 degree there. And there is no nose radius almost, there has to be 0 nose radius. It's a very sharp tool. It doesn't matter why do you need a microscopic tool. You have to turn a shaft of 50 micron diameter. You don't need to, the tool can be macroscopic, what is wrong in that? But the tip is very sharp.
And cutting tool will recur or no?
Cutting fluid, that's what I say. No, whenever the part feature is not the feature alone, it is the part itself is very weak, very delicate. Like it's a cantilever, no, it can just deflect. So it is better you should either use MQL or might be a shielded. There are two solutions. Cutting fluid is better to avoid it. Yeah.
How the ECDM helps in the micro rendering?
ECDM is helping in the micro to make the substrate. You are making the rod, carbide rod of 50 micron. 50 micron rod by the turning process is very difficult. As long as 300 micron, 400 micron it can be done. But EDM, what is known, it is a contactless. It is just a crater and the crater is created by the spark erosion, evaporation of the material. So literally the mechanical force is absent there. So that is the reason that form deviation. If there is a mechanical force, there will be deflection. If there is a deflection, there is a compromise on the depth of cut. So the form accuracy is very difficult to maintain it through the turning. But if you do the EDM, the form accuracy is fantastic. But it is not a wear EDM is not that much good. It has to be a strip EDM or might be a disc EDM. So like one strip, one rod is here and not a wear, the other is strip. So it will rotate and it will do the wear EDM machining and it will keep on moving. Otherwise you cannot control the surface finish. So EDM is used for making the substrate. After that you have to use a bonding system to join the superabrasives on that. So that is the thing. Yeah.
Sir, with the help of that electron beam ablation, can we
Laser ablation we do. Electron beam ablation can be also done.
yes, can we control the rectangle?
Yes. Because electron beam on laser beam is fixed. You can have the stages, rotary stage and XYZ stage, and you can rotate it and you can.
In those grids we can do.
Not grids. This is what I said that it is a coating. You have a 500 micron rod, on that you have a 10 micron CVD coating. That coating you are texturing and you are ablating the coating material in such a way that every point will become like a single point turning tool, single point milling tool.
Okay, that coating we can actually give the rectangle and
Coating will not give. The coating apparently it's a smooth. And again I am saying apparently why if you magnify it there is also an ups and downs. Okay, I just assume it is very nanometric scale smooth. What they do after that you can cut and you can say you will have a thin film. You can just
make the texture.
make the texture. The texture whenever you are making you just don't make the roots. Along with that the top surface also you ablate. So that it gets a form of it. Every point will become a single point cutting tool. That's an amazing thing actually. But that is the tool which is the most perfect tool. Because all tips are at the same radial points and you have very less specific energy consumption because they are favorable to geometry. But they are diamond. They are SP3 diamond because you are using the diamond CVD. There is no graphite, there is no DLC coating. This is pakka pure diamond. But you are ablating the diamond in the layer.
Any other question? Sir, is treatment necessary after electrolysis coating?
No, because heat treatment is going to cause problem only. Because heat treatment is, the substrate.
Some of the coating treatment is done.
No, electrolysis coating, the temperature may be necessary to facilitate the chemical reaction. That much only, but that is very low. Temperature is not good for making for any tool. Say, I just need to tell you one thing that even you can do by the brazing technology. You can braze the diamond and silicon. Actually, that is my current area of work. We are making the tools, micro tools. We are going to make the micro tools with the brazing the diamonds on the periphery. That brazing takes place at a high temperature. You join diamond to steel at a high temperature, or carbide at a high temperature, but then you have to cool it, no? During the cooling, diamond will cool at a different rate, the substrate will cool at a different rate, and there will be residual stress. While you want to grind, that will be cracked out. So that is the major problem in the brazing. So micro grinding, I don't know whether the brazing is that much good or not. We need to check it out. But people are trying out, people are reporting. But unfortunately, the engineering reports you should not trust too much. If you read a paper, please look at which university is publishing, which group is publishing. That is very important. Because all sorts of nonsense things are getting published, I should say. If you just follow that things, you will end up in trouble because in understanding and your overall knowledge. So it is very important that the person who is publishing, which group is publishing, which university is publishing, depending on that. I am not telling everything, but a lot of junk things are coming. Right? It is not like that always the good university publishes everything. There are even the smaller universities which do wonderful things. But the thing is that finding out the diamond from the mines of the coal is really difficult. But we can always hope for the best. But if you read a paper, you understand that whether the strength is there, whether the group has the good understanding or not. That is very clear. So I can tell you one thing, my first paper on joining of the diamond, we published that there is a crack at the root of the diamond if you want to join the diamond with the steel. That paper got rejected because they say the diamond is not, it is impossible that there is a crack at the root. And people are using the brazed diamond tools, how they are using it. See, you can sustain something, you can do something with your impaired hand also. So if you have a minor fracture, but still you can do some more, no? But if your fracture is not there, you can do the better work. So then we had to submit literally 6-page doodles, and then the paper got published. And that paper is having the very high citation rate. You cannot believe within 5 months or 6 months, there are n number of papers coming out from one of our neighboring countries reporting that there are the cracks. Right? So genuinity is very important. I would request those people who will be doing the research, please feel whatever is genuine, please try to report it. Otherwise, the research community may get misled. It's very important. Thank you so much. Thank you for your patient hearing, especially the voice. I think might be something it was little bit of high end, but I tried to explain from a very basics. I didn't use very high end terminologies because I assumed that a major portion of the students, at least 10%, at least 50% of you find some interest into that. My job is done. And at the last, I just want to a little bit to advertise for my own university, my own institute. You know IIT Madras very well, number 1, NIA ranking for the last 6 years. We are very well ahead of all other universities in terms of the research in the manufacturing, especially the experimental manufacturing in mechanical. And please do appear. I see a lot of people who appear for the direct PhD applications and then or MTech or MS program. MS program is a very popular program in the IIT Madras. Please look into that. You see that even if you have a GATE score little low, we really do not look into the GATE score to that extent. We do regard the GATE score, we do respect, but at the same time we do believe that many people do not take GATE seriously. And to be very frank, a majority percentage of the top runners, they really don't bother about the GATE. But they do realize that it is good to have the higher studies, but they realize after joining the industry. So we keep an option open. So if you have a good academic career, if you feel you are a bright student, you can enroll for the MS program. And if you have a decent GATE score, even if it may not be very high. So what happens now, you get a chance for the research program. You take coursework related to the field, whatever you will be picked up. Most of the problems are linked to the industry. You will get a lot of opportunities to the industry. You cannot believe my last 3 scholars, they are working in the industry. 2 PhD and all MS scholars, they went to the industry, except one who is eventually from your Institute of Technology. He is now doing PhD and PhD abroad. But most of the MS students, they go to the industry, and now the PhD students are also going to the industry. My last student is in Omnicool, you might be knowing that's a startup company. Another person is working in the same domain. And recently another company is in the coding company. So it is not like that you don't have any other option, you come to the PhD. Absolutely not true. Take it up seriously, you inquire. So I'm available. You know my name. Drop me a mail. I'll be happy to reply you back if you have any query related to even your career in the academics and research, of course. Don't ask me about the finance. I should go to finance or academics. I'm not the right person to answer you in that case. Thank you so much. Thank you for your patient hearing, and thank you both for the data. And I once again convey my gratitude to the principal, so that I get a privilege to present some of the good works which is happening all over the world, and I'm happy that at least majority of you are joining. Thank you so much.
Thank you, sir. Now I'd like to request Professor Jana to summarize the session.
Good morning. Thank you, Professor Amitabh Ghosh from the Mechanical Engineering Department of IIT Madras. It is our good fortune that today we had the opportunity to be enlightened with his lectures, research work, state-of-the-art research work in the area of grinding and micro grinding. He had started with the very basics of grinding, the physics of chip removal, other associated parameters, that is the cutting force, speed, depth of cut, torque, cutting velocities, and finally he has enlightened us with the state-of-the-art development in the micro grinding areas, different technology associated with it, different materials, challenges, and the solutions. I would like to convey my sincere thanks to the coordinator, Professor Gautam Ghosh, to identify and invite Professor Ghosh. And I believe that in this 2 hours lecture, all of us, particularly myself, is extremely benefited, and the words, additional words he has uttered during his lecture, that we focus or emphasize on the fundamentals of the related topics, so that we can have a solid foundation, and then we can move forward with the other research activities. I once again would like to thank and convey my sincere regards to Professor Ghosh for taking the pain to travel over a long distance from Chennai to Kolkata yesterday night and today morning. Within 9:20 he has reached our department, and for the 2 hours uninterruptedly he has delivered his speech. So I believe that this is a very fruitful discussion, and he has enlightened us with varieties of inputs and the latest research developments that are taking place in the area of micro grinding and the associated related areas. I believe that participants, students, faculty members, all of us are extremely benefited, and in coining with his remark that we should carry forward our work with these inputs whenever it is possible, and these are not too far with the latest development, these micro machining, micro grinding advancements which are confined to the specific area will be also spreaded like anything else, and we will be able to we will be able to derive the benefits of the research contributions like people like Professor Ghosh. Thank you very much.
We are almost at the end of the session. Just bear with us the first call formalities. So I'd like all the participants to come up on the stage for